Good morning, students. In today's video, we are going to see regarding the design of beams. In the previous videos, we have seen the analysis of beams. We have seen different types of beams also. Further, we are going to study regarding the design of beams. So, let us start now. So whenever we are going to have any framed structure, we are going to have number of structural components. We are going to have beams, we are going to have columns, we are going to have footing, or we are going to have slab. The next is as a structural designer, we have to think, like for example, if you are designing this beam, so which type of beam it is, whether it has to be designed as a rectangular section or a flange section, that is T shape or L shape. It depends upon the structural engineer. So he has to think over it, and it has to be designed accordingly. The next is that design of the beam is nothing but we are going to fix the dimensions of the beam. So for example, if you see this frame itself, so this is one column we have, this is another column we have. The length between these two columns will be fixed. So therefore between these two columns we are going to provide the beam. So as far as length is concerned, length will be fixed, we need not worry regarding length. Next is we have to fix the cross sectional dimensions of the beam. That means if you see this beam, what is the width of this beam and what is the depth of this beam, what is the depth of this beam. So that has to be fixed by the structural engineer. And what reinforcement you are seeing here, what reinforcement you are seeing it here, whether what reinforcement has to be provided at top, what reinforcement has to be provided at bottom, what can say, stirrups has to be provided. These stirrups what you are seeing in the figure, so what has to be provided, it has to be decided by the structural engineer. He has to design this beam. Length will be fixed. So next is we have to fix the cross sectional dimensions of the beam. That means you have to fix this width of the beam, we have to fix the depth of the beam, and we have to provide the reinforcement as per the IS codal provisions. So this is what we do. This is nothing but this is the aim of the design. The aim of the design is to decide the size or dimensions of the beam and to provide the suitable reinforcement. Then next is the section what we are going to design. It should perform satisfactorily during its lifetime. And as you know, beam is a flexural member, so basically it is going to resist loads by bending. We are going to have different types of beams, already we have studied, that is singly reinforced beam and doubly reinforced beam. In singly reinforced beam we are going to provide the steel reinforcement in the tension zone, whereas in doubly reinforced beam we are going to provide the reinforcement in tension as well as in the compression zone. So already we have studied, so this thing itself will apply. So now let us come to the design procedure. What is the design procedure what we are going to follow? So basically like we are going to, first thing is we are going to estimate the loads. Then next is after estimating the loads, we are going to analyze that beam from this estimated loads. Then next, after getting shear force and bending moment, based on that we'll try to design the section. So this is the basic outline what we have so as to design a beam. So let us see one by one now. First one is estimation of load. That means what load is going to come on the beam, that has to be calculated. So what happens is that generally the load that is going to act on a beam, it consists of the following. First one is that self weight of the beam. So whenever you take any beam, so it is going to have its self weight, so that self weight has to be considered. Then next is that weight of the wall constructed on the beam. So usually what happens is we are going to construct the wall above the beam itself. So therefore what is the wall load that is going to come, so that has to be calculated. So how to calculate now? So based on the what is the width of the wall and what is the height of the wall, so based on that what is the UDL or load that is going to come on that beam, so that has to be calculated. Then next comes is what is the dead load, live load, etc., that is going to come from the slab. so that has to be calculated. So for example, if I am going to take, I have one slab now, I have one slab. So for example here, I have one beam now, so this will be one beam for example. So what load we are going to put, how much load we are going to have on this beam, and how much load is going to come on this beam, so that has to be calculated. So proportionately the load which is going to come on this beam, that has to be calculated. That loads might be the dead load, or the self weight of the slab, or the floor finishes you may have, or the live load which is going to, for which the structure is being designed. So that load has to be transferred on this beam. So from based on this load, what we can do, we are going to design the beams. Right. First one is estimation of loads. The next comes is analysis. After getting all the loads on the beams, after estimating the loads, what we do is that we are going to analyze that beam. So in the previous semester, like they used to give you one beam and all, and they used to give certain UDL, or they used to give certain point load, many things they used to give. So for that already we have analyzed those beams. That means we used to calculate like a bending moment, or like a shear force we used to calculate. So similarly, what happens is that there are many methods already which we have studied. Based on that, what we do, we are going to calculate the shear force, bending moment, or based on these loads. So analysis can be done by any other methods, any method, or like nowadays what we do, we are for using softwares also. But in your subject, we are going to manually calculate what you can say shear force and bending moment. Then next is that after getting the shear force and bending moment, what we do is that we are going to go for the design of that beam, design of the beam. So now how to design the beam? So we will see step by step. There are number of steps what we are going to follow. First one is that selection of the width and depth of the beam. So if you take any beam, for example, if we are going to have one beam, so it is going to have certain width and it is going to have certain depth. So first aim of the designer is that we have to fix what should be the width of the beam and what should be the depth of the beam. So now first let us see this width of this beam. So the width of the beams shall satisfy the slenderness limit specified in the IS 456 2000. So usually what happens that the breadth of the beam shall be one third to half the depth. One third to half the depth. Minimum being 200 mm or 230 mm. So generally what happens is that here in Bijapur, if you see, we are constructing 230 mm thick wall. So that is 9 inches and all. So we are going to keep the width of the wall, that is equal to 230 mm. Why? Because what happens that it will be in same line, or it is going to get flushed with the wall. So we are not going to have any offset. It doesn't look odd. So therefore what we do, we keep it as 230 mm. So if you are going to have a blocks of size 200 mm, so that time we can fix the, what you can say, the width of the beam as 200 mm, but breadth of the beam shall be one third to half the depth, minimum being 200 or 230 mm. Accordingly we have to fix the dimension, that is 230 mm, 200 mm, 250 or 300 mm, or so on. Then next comes is this depth criteria. So usually the depth of the beams shall be 112 to the 1/15th of the span. 112 to 1/15th of the span. So we have to fix the depth in this way. This is nothing but breadth and depth, what we are going to fix based on this criteria. So usually what happens is that beam usually it carries the vertical loads, but if the length of the beam is very large, so it may bend laterally also. It may bend laterally also. So therefore what happens is that so as to avoid the lateral bending, it has to satisfy the following criterias. It has to satisfy the following criterias for a simply supported or continuous beam. So they have given in the IS 456 2000, that is 23.3, clause number 23.3. So they have given is that the clear distance between the lateral restraint shall not be greater than 60 times of B, where B is nothing but the width or 250 times of b square divided by d, where b is nothing but the width and d is nothing but the depth. So out of this, whichever is less, the clear distance between the lateral restraint shall not be less than this or this, whichever is less. This is for a simply supported beam or for the continuous beam. So this is the case when it is going to bend, when you have length of the beam is very large, when it is going to bend laterally. So as to avoid this, so this criteria has to be satisfied. This clause has been given, what you can say, in the IS code, that is 23.3. Here they have given in 23.3. You can see here 23.3, that is slenderness limit for beams. So this is what just now I had shown you, that is the distance between the lateral restraint does not exceed 60 times of b or 250 times of b square by d. Then next comes is for cantilever beam. So for cantilever beam, what happens is that the clear distance from the free end of the cantilever to the lateral restraint, for example, if this is the column we have and this is the beam we have, so from the free end of this cantilever to the lateral restraint what we have, so this distance shall not be greater than 25 times of b or 100 times of b square by d, whichever is less, where b is nothing but the breadth, d is nothing but the effective depth. This is also given in the code book itself. For a cantilever beam, it should not exceed 25 times of b or 100 times of b square by d, whichever is less. Then next we will go to, after fixing the dimensions, we'll try to go for the calculation of the effective span. So this also already it is being given in the code book, that is 22.2 IS 456 22.2. So what happens is that for a simply supported beam, effective span will be equal to clear span plus effective depth. Clear span plus effective depth, or center to center distance between the supports. So least of these two will be the effective span. This is being given in the criteria 22.2. So if you see 22.2 here, they have given that is nothing but effective span. For a simply supported beam, it is given as the effective span of the member that is not built integrally with its support shall be taken as clear span plus effective depth of the slab or a beam, or center to center distance of the support, whichever is less. Whichever is less. So least of either this or least of either this. So that will be the effective span for a simply supported beam. So when we have a continuous beam, so the effective span for a simply support is same if width is less than 1/12 of the clear span. Or next is for end span with one end simply supported and other end continuous. If you have a continuous beam, one end is simply supported and other end is continuous, that time the effective span will be equal to clear span plus half the depth, or clear span plus half the width, whichever is less. In the case of roller support, so clear effective span will be equal to center distance of the bearing. So for example, if you have a beam, so if you have a roller support, so distance between this center to center distance of this bearing what we have. Then next is in case of cantilever, so effective span. Now this is the effect, what you can say cantilever, what you can say we have. So here the effective span will be equal to center to center of the support to the free end, center of the support. So you can see here this is the support we have. So from the center of the support to the free end, this distance will be nothing but the effective span of the beam. So all these things already it is being given in the code book itself. So continuous beam or a slab, so 1/12 of the clear span, this is given. Then next is that for end span with one fixed and one end fixed and other continuous. So for just now what all things I have said, so all those things for roller support and all, for end support with one and free, other continuous and all those things in the wordings already what I have explained, it is being given. And for cantilever also it is being given. So based on these criteria, we are going to calculate the effective span of the beam. Then next, after calculating the effective span, we what you can say, we are going to estimate the loads. We are going to estimate the loads. After estimating the loads, we are going to calculate the critical moment and shear. We will try to find out where we are going to get the maximum bending moment and shear force, and we are going to calculate the factored bending moment and shear force. After finding out the factored bending moment and shear force, we are going to check for depth based on maximum bending moment. So based on this bending moment, we are going to check the depth what we have provided, whether it is satisfying the requirements or not. If it is not satisfying, we are going to revise the section. So after calculating this, after checking, what we do is that we are going to calculate the steel quantity. We are going to calculate the steel quantity. So after that, what we do, there are few checks what we do. So one check is that we are going to check for shear. So in the earlier classes what we have done, seen for shear, so same thing we are going to check it for the beams. Then next is another check is that we are going to check for the development length. This also already we have seen, same thing we are going to do further. Then next is that we are going to check for deflection criteria also. After that, we are going to check for maximum and minimum area of steel that has to be provided in the beam. So minimum, if the reinforcement required is very much lesser, then also what has to be done is that we have to provide the minimum area of steel. So minimum area of steel will be equal to 0.85 times of B into D divided by F of Y. So this is nothing but the minimum area of steel. This is being given in the clause 26.5.1.1. So if you see here they have given 26 point, what you can say, 5.1.1 they have given. So you can see here requirements of for reinforcement for sectional member beams. Minimum reinforcement shall not be less than, they have given AS by BD is equal to 0.8 F of Y. So AS will be equal to BD, you can bring it this side. So therefore this is nothing but the minimum area of tension reinforcement. Minimum this much steel has to be provided. Then next is that where B and D are nothing but the breadth and depth, and F is nothing, Fi is nothing but the characteristic strength of the reinforcement. Then next comes is the maximum reinforcement. The maximum tension reinforcement shall not exceed 0.04 times of B into capital D. So capital D is nothing but the overall depth. So maximum reinforcement AST max, that is equal to zero point zero 0.04 times of B into capital D. So this is as per IS code 456 2000 clause number 26.5.1. Then next comes is regarding the side reinforcement. So regarding this also it is being given in the code book 26.5.1.3. So when the depth of the web in a beam exceeds 750 mm. So for example, if we are going to have one beam, so this is the slab for example, and this is the depth we have. If this depth of this web, if it is going to exceed 750 mm, if the depth of the web in a beam exceeds 750 mm, if this is greater than 750 mm, then next we have to provide the side reinforcement along the two faces. That means here we have to provide the side reinforcement on the beams. So usually what we do, the reinforcement it is going to be provided at the top as well as at the bottom. But when the depth, if it is going to increase or if it is more than 750 mm, so side face reinforcement equally it has to be distributed on the sides, and the area of that shall be zero point 0.1 times of B into D divided by 100, which has to be distributed equally on both the faces, and the spacing of those shall not exceed 300 mm or web thickness whichever is less. Then overall if you see, this is what we do, these are the design steps. Once again we will revise it. So first thing is that now this is how we are going to do design. In the further video we'll see. So first what we do is that we are going to fix the overall depth required, that is capital D we are going to fix. Based on that we are going to calculate the effective depth. B and D we are going to fix. Then next is we are going to calculate the effective span. So already just now I have covered regarding the effective span. After getting the effective span, we are going to calculate the loads. We are going to estimate the loads. What load is going to come. Based on that load, we will try to calculate what is the bending moment and shear force. There are a number of methods what we can follow. Then next to that, we are going to check for depth, whether it is satisfying this bending moment and shear force. Bending moment. Then next is that we are going to calculate the area of steel required for a given bending moment and shear force. Then next, after calculating the area of steel, we are going to check, there are few checks what we are going to do. One is we are going to check for shear, check for deflection, and check for the development length. So we'll check it whether it is satisfying these criteria or not. If not, probably we are going to change the sectional dimensions or we are going to increase the reinforcement so as to satisfy these three checks. So after doing all these things, at the end we are going to do the detailing of the beam. That means we are going to do the prepare a sketch wherein we are going to show the dimensions of the beam and what is the reinforcement which is provided at the top and bottom. That is what we are going to show.